Now we're going to talk about where matter came from, how we went from the explosion of the Big Bang to all the stuff that we see around us today. So, in the universe, the most common element is hydrogen. The third most common is oxygen, and the fourth most common is carbon. Now these are all elements essential for life as we know it. But why? Why would they be up there in the most common elements? So let's start. First looking at hydrogen, where everything came from. So after the Big Bang we had the huge explosion of energy leading to the formation of quarks and antiquarks. And somehow there were a few extra quarks than antiquarks, so we had matter left over. These quarks came together under the strong nuclear force to form protons and also some neutrons. So hydrogen, which has mass 1, is simply a proton. It can have an electron around it. Now, as stars began to form, the furnace, the driving force of stars, was hydrogen being converted to helium, which has mass 4. And so what happens is you have the proton from hydrogen, and then two hydrogens then come together to make mass 2. And then a third hydrogen comes in, and then a fourth hydrogen comes in, to eventually get to mass 4, which is helium. And so it's the strong force that dominates, that allows these two protons to come together and to bind together to form a heavier element. And then it's the weak force that converts the protons into neutrons, so that the helium, which is 2 protons, can also have its 2 neutrons for a total of mass 4. And so this is kind of what stars do. It's where their energy comes from. And you would think it would just keep going on up from there. You start with mass 1, mass 2, then mass 3, mass 4 is helium, and you go up mass 5, mass 6, mass 7, all the way till you get to the heavier elements that we need and that we see today. But that's not what happens. There's no mass 5. So how do we get to the heavier elements if there's no mass 5? That pathway is dead. Well, what can we do? Eventually, all the hydrogen burns up in a star, and all there is helium. So the star is stuck. Where can it go next without the mass 5? Well, it can try to bring 2 heliums together, so 2 4s will make a mass 8. The problem is this mass 8 beryllium, as it's called, is incredibly unstable and doesn't work. But what if you bring 3 together? If you bring 3 together, you would get carbon. Now that might explain why carbon is so abundant, because then if you brought a 4th helium in, you would get oxygen. Hey, that could explain the abundances of why oxygen and carbon are so much more abundant than a lot of the other elements in the universe. But can we do this? To bring 3 things together, first of all, requires a really high temperature. But if you get stars hot enough, that's no problem, that's doable. But you also have to bring these 3 particles together all at once. Because if we remember, we can't just bring 2 and add a third, because that mass 8 beryllium will disintegrate. And so that's really hard to do. And no one could figure out how it was done. The physicist Fred Hoyle was very confused by this, because he knew there's a lot of carbon in the universe. There are heavy elements. We exist. We're made up of mainly heavy elements. So they had to come from somewhere. So he predicted that carbon must have some sort of resonance that allows it to form. Now, a resonance is like this. When you have an opera singer who sings a very high note, sometimes that can have the exact same frequency as a crystal glass has this characteristic frequency that it likes to oscillate, it likes to vibrate at. And so if the singer hits just the right note, the glass and the note from the singer will begin to oscillate really fast and the glass will shatter. The same thing happens when you listen to the radio. You actually change the frequency and the antenna that it hits that special vibration at until you get to the one of the radio signal. So when the radio signal, which has a frequency, matches this special resonance frequency of the antenna, it vibrates really fast and you get sound out of it. Hoyle predicted something similar for carbon because matter has wave-like properties. And so he predicted a resonance in what's a high energy state, a place where the electrons can be. That would perfectly make it just favorable enough that the 2 heliums would hold together just long enough to bring a third in. Now he hadn't observed this, he just predicted this must be the case because we see carbon and we have no other way to get to it. Sure enough, some years later that exact resonance was found to be in just the right place to allow carbon to form from 3 heliums coming together. And that resonance is determined by a precise interplay of the strong force and the electromagnetic force, putting it at just the right place. Okay, so now we have the formation of carbon. So from there, things are relatively simple. We get carbon, and then we can add another helium to get oxygen, which is another one of the more common ones. Then we can go up from there. We can go up to neon and beyond that. And then we can use other processes to get some of the other elements that are in between. So now we have a rough idea of why hydrogen would be the most, and then we also see large amounts of carbon and oxygen. But then how did they get to us? How were we formed? These are all formed in really hot stars that have burned out of their hydrogen, first to helium, and now converted to the heavier elements. So eventually these stars begin to die, but if they're really large, they can become something called supernovas. So supernovas, the star begins to collapse in on itself and slowly die. But supernovas are so big that their energy inside them causes them to explode outward, shooting all their heavy elements out into the universe. And those heavy elements eventually could coalesce to form things like planets in our solar system and Earth and lead to forming us. And so we are actually stardust. We are made up of matter, of elements that were formed as huge stars and spewed out in supernovas. Now something interesting here is that those neutrinos that we talked about play a really interesting role. So as the star collapses in on itself, it becomes incredibly dense, and it forms a lot of neutrinos, and the nuclear process is going on. So there's tons of neutrinos inside here, but because it's so dense, even the neutrinos have trouble getting out, have trouble getting through. And so this pressure of neutrinos builds up and eventually causes the explosion that forces it outward and sends all the material out into the universe. And this is dominated by the weak nuclear force. And so if the weak nuclear force was weaker than it is, there wouldn't be that explosive push to push all the elements out in a huge explosion. But if the weak nuclear force was stronger, then the neutrinos would be interacting with the other particles normally, and they would never be able to generate that buildup to generate the explosion. And so we see here again that neutrinos, something very small, pass through us all the time, and yet they play an important role in allowing us to exist in the first place.